So let's translate them. Because, well, we have to translate that to algebra. We have to relate those to all those conditions to x's, y's, m, and b. So the simplest thing is to translate this point. So what's the point? The point has coordinates. Well, the line has equation y equals mx plus b. And therefore, this point has coordinates 0, b. So P has coordinates 0, b. What about all those strange things like Fi? What can we say about Fi? What can we say about the force that the spring exerts onto the line? And what is it here that we can relate to those x's, y's, and m and b? So the point where the nail is the point xi, yi. Right? You know that. Is there anything we can say about this point where the spring is attached to the rod? It has, since I made the spring vertical, it will have the same xi coordinate. And so this point will have coordinate xi. And what would be the y coordinate? This one? This is the point of, well, given by the data. The original points were xi, yi. So this is where my nails are, this is where I want the line to go through. And then this point on the line is determined by the equation of the line. So the coordinates there are xi and mxi plus b. And then I know exactly how the spring is stretched. I know exactly the length of the spring. The spring number I has length. What's the length? Xi plus b minus yi. The difference of y coordinates. And then, if the spring is that long, what will be the simplest way to set up the force? Won't it be the force is equal to some constant k times the length? I remember the Hooke's law about stretching the spring. And then this k comes in, right? Because technically k is the constant related to the spring, depending on the properties of the material, right? Well, we probably want all the springs to be the same. So we probably want this constant to be the same for all the springs so that we don't artificially distinguish one point from the other. We don't make one point more important than the other. So they're all equally important for us, so all the constants are going to be the same. It will be one constant k. And then what? Well then, well, this is not a vector yet, right? Well, I know the vector is vertical, so it will have coordinates 0 and that number. And then I can now make the first equation. The net force equals 0. That equation says that the sum of all those vectors 0 and k times mxi plus b minus yi must be 0. What does that mean? Can we simplify that? Well, if you add all the vectors, all the first coordinates are 0. And some of those zeros will equal to 0 anyway. Right? So the only condition, non-trivial condition, is coming from the second coordinate. And the condition says that the sum of those quantities, k times mxi plus b minus yi, equals 0. Should we check against what we had before? Is that a good condition? Is it the one we experienced previously? Is this the one? Well, because this k is the same for all the summands, so you can pull it out of the sum. And since the whole thing is supposed to be 0, you can cancel it. So the whole condition effectively is that the sum of all these quantities is 0. And that is something we had there. Alright, that's a good thing. What about momentum? How to compute the momentum? What's the momentum of that force with respect to that point? How do you compute the momentum? You have a point, you have a force, and here's the vector of the force. What's the momentum? Force times perpendicular distance. So you multiply the magnitude of that force by what? You extend that line of the action of the force, and you look at the distance perpendicular. Right? And can we compute all that? Each force, let's say force Fi. This point is, well, I can make it origin. Why not? Let's make it origin. What's the momentum of all the forces with respect to origin? What's going to be the perpendicular distance to the line of action of the force Fi? Xi. Exactly. So this is Xi. So I will have to add all these momenta, and each momentum is Xi multiplied by what? By the force Fi. And the force Fi, the magnitude is right there. It is k times xi times k times mxi plus b minus yi. That must be 0. And again, I use the same constant k in every summand that can be factored and cancelled because we have equation equals 0. So after you cancel, don't you recognize something? It's exactly the second equation. So geometrically, this equation means that the vector x is perpendicular to the error vector. Algebraically, it means that the partial with respect to m is 0. And in physics, it says very precise thing. It's the momentum that equals 0. So, the physics doesn't miss anything. Isn't that good? And one condition that we had, that gradient equals 0, or that the error is perpendicular to the plane, can be described in physics. It's the statement that that solid, that rod, is in equilibrium. And you immediately interpret that as net force equals 0 and net momentum equals 0. So for this case, we have complete correspondence of all these points of view. Nothing is missed. Isn't that good?